When we started our discussion of kinetics, we talked about kinetics being the study of how fast chemical reactions occur. And we also talked about them being the study of how reactions occur. So now in our next couple of videos, we're going to move into that discussion of how as we take a look at mechanisms. Now, chemical reactions that you have dealt with so far in your chemistry courses are what are called overall reactions. These types of equations summarize the reactants and products that are used for stoichiometric calculations. They tell us nothing about how the reaction occurs. So they're just telling us what we started off mixing, and they tell us what we end with, but they don't tell us what happens in between. They don't show the individual steps involved, and there's usually more than one. So a mechanism is going to be a pathway or sequence of steps by which a reaction occurs. These mechanisms indicate what particles collide as new bonds form and old bonds break. Mechanisms are determined by experiment and rate information. So what do we care about mechanisms? Why are we studying these? And the reason we study mechanisms is because they allow for better control of reactions. They help us to maximize our yields. They help us prevent danger. We can speed up or slow down certain steps if we understand what's going on in those steps, and they aid in predicting new reactions. So when we look at a mechanism, and we can express mechanisms a couple of ways, but they're going to have some primary key components. They're going to consist of elementary steps. So these are going to be the individual listed steps in the mechanism. So what is interacting with what at what stage? They're going to indicate intermediates. So intermediates are going to be components that get formed during one step, and we turn around and use them in another step. They very often do not appear in our overall equation. We may also see catalysts. Catalysts can be, in terms of a mechanism, can be components that get added or used in one step and get reformed in another step, in a later step. And then finally, we have our overall equation. That is the sum of all of our elementary steps. So we can look at an example. The following mechanism represents the reaction of NO2, so nitrogen dioxide, with carbon monoxide, producing nitrogen monoxide and carbon dioxide. So that equation is what we would have used in a laboratory. If we've gone in the lab, we mixed the nitrogen dioxide and the carbon monoxide. Those are the reactants we started with. In the end, we end up with those products, and that's the equation we would have used for stoichiometry. But what this is indicating here to us is that this reaction occurs in multiple steps. This is telling us that what will have to happen, because even though we've got that reaction written, so there's one NO2, that's the mole ratio. In reality, we have got more than one single NO2 molecule and more than one CO molecule. So we've got multiple molecules around that could interact with one another. So this is indicating that what would have to happen is the NO2 would react with another NO2 molecule. That's going to result in transferring an oxygen. So we're going to have one of the oxygens on that NO is going to get transferred to the NO2, forming an NO3 and NO. It's the NO3 that turns around and reacts with the carbon monoxide in step 2 to produce NO2 and CO2. So in this setup, steps 1 and 2 here, these are our elementary steps. Bottom equation here, it's the sum of those steps. So if we're adding chemical reactions together, what we do is we cancel atoms that appear on both sides of our arrows. So I have an NO2 here and an NO2 there. Those are going to cancel. I have an NO3 here and an NO3 there, so those cancel. So that just leaves us with the NO2 reacting with the CO. So that's what we see here in our overall equation, NO2 plus CO, producing NO plus CO2. So that's my overall equation. It is the sum of those elementary steps. Now, other components of our mechanisms that we could see would be things like an intermediate. An intermediate, we said, was going to be something that gets formed in one step and used in a later step. Here in this mechanism, the NO3 is an intermediate. We produce that NO3 in step 1. And then we turn around and use it as a reactant in step 2. So that NO3 is an intermediate. And again, notice that it does not appear in that overall equation. So with problem 1 here, this is giving us practice with writing overall equations, identifying which species are intermediates or catalysts. So again, if we're going to determine our overall equation, we're going to add up our elementary steps. When we're adding up those elementary steps, we are canceling things that appear on both sides of our arrows. So I see I've got an Mn3 plus as a product and as a reactant. So that Mn3 plus cancels. I have an Mn2 plus as a reactant and as a product, so the Mn2 plus cancels. I have Mn4 plus as a product and as a reactant. The Mn4 plus cancels. So that's going to leave me with the Ce4 plus. There's 2 of them, so I'm going to have 2 Ce4 plus. And then I have my TL plus. And then over on my product side, I've got the Ce3 plus, so there are 2 of them. And then I have the TL3 plus. So that's my overall equation. That's indicating what we start with and what my net change is going to be. So then we're asked to identify any intermediates. So again, our intermediates were going to be substances that we formed as a product in one step. We turned around and used it as a reactant in a later step. My Mn3 plus was an intermediate. We formed it in step 1. We turn around and used it in step 2. Now that is not my only intermediate. I also have the Mn4 plus. The Mn4 plus we formed in step 2. And we turn around and used it in step 3. So I have 2 intermediates here, the Mn3 plus and the Mn4 plus. Then we're asked to identify any catalysts. So catalysts are going to be, when we're looking at a mechanism, something that we added in an early step and it got reformed in a later step. And in this case, that's going to be the Mn2 plus. We used it as a reactant in step 1, and it got reformed in step 3. So we didn't use it up. We put it in. It went through a couple of changes, but then it came back to its original self, so we got that Mn2 plus exactly back as it was. And so it's not being used. So that Mn2 plus, we used it in step 1. It reformed in step 3. Now, when we talk about our elementary steps, the elementary steps can be described by something called a molecularity. The molecularity indicates the number of reactant particles involved in each step. A step is described as being unimolecular if it involves only one reactant. So here we have the example of A producing products. So A is not interacting with anything else. It's not interacting with another particle of A. It's just randomly breaking apart into something else. A bimolecular reaction or step involves two reactants. So we have two possibilities. It could be A interacting with A, so two of the same substance colliding to produce products, or it could be two different substances, so A plus B producing products. And then finally, we could describe a step as being termolecular. That would involve three reactants. These are going to be rare, but it could be an example of A plus A plus A producing products. We could have A plus B plus C producing products. And we can have many other variations. Termolecular is going to be rare because for that reaction to occur, remember our particles have to collide. Not only do they have to collide, but they have to collide in the right orientation so that the right things are interacting. When you have got more particles, the statistical chances of them colliding in the correct manner becomes much lower, and therefore those reactions become much harder. So we want to take a look at our mechanisms and identify their steps as being either unimolecular, bimolecular, or termolecular. So if we look back at the mechanism we had in problem 1, we're asked to determine the molecularity of each step. So if I look at step 1, I have Ce4 plus Mn2 plus. I have two things interacting, so that's a bimolecular step. Step 2, Ce4 plus Mn3 plus. Two things interacting. That is bimolecular. Mn4 plus Tl plus. Again, two things interacting. Bimolecular. Now, all of these were scenarios of an A plus B, so two different things interacting. But if we go back and we take a look at our very first mechanism, here I've got NO2 and NO2. So the fact that we have NO2 plus NO2 indicates that two particles have to collide. That is a bimolecular step. But that's what we're referring to as an A plus A scenario. So two particles of the same type of substance colliding. So looking at problem number 3, we're going to continue to get practice with writing overall equations, identifying intermediates, catalysts, and now we're adding in that molecularity. So we're asked to write our overall equation. We've got this 3-step mechanism. We look to see if anything appears on both sides. I see that I've got chlorine here as a product in step 1, and I've got 2 of them. It shows up in step 2 and in step 3, so that chlorine cancels. I also have a CCl3. The CCl3 and products and reactants cancels. So that's going to leave me with Cl2 plus CHCl3 producing HCl and CCl4. So that's my overall equation. We're identifying any intermediates. Again, we're looking for things that are going to be things we canceled out. So an intermediate is something, again, that we formed in one step and it was used in later steps. So one of my intermediates is going to be chlorine. It was formed as a product in step 1, but we turned around and used it in step 2 and step 3. So that chlorine is an intermediate. We have another intermediate, the CCl3. The CCl3 was formed in step 2, and then we used it in step 3. We're asked if we have any catalysts here. So catalysts, we're looking for something that we added in one step and it got formed again in a later step. In this particular scenario, we don't have anything that we added as a reactant in one step and formed as a product in another. So there are no catalysts in this mechanism. So going through and determining our molecularity. Step 1, I've got Cl2. It's not interacting with anything else. It's simply breaking apart. That is a unimolecular step. Because it's just one molecule of Cl2 breaking apart into those chlorine atoms. Step 2, I've got chlorine atom plus CHCl3. I've got two things interacting. That is bimolecular. Step 3, chlorine plus CCl3, two things interacting. That is bimolecular. So our mechanisms share key components. They've got elementary steps that add together to give us the overall equation. If we've got multiple steps, we usually will have intermediates, and we may occasionally have catalysts. Each step is described by a molecularity depending on the number of particles that interact with one another.